There we go, back at it. It's so weird to not have Zoom in front of me. Like, I'm still looking at my camera every 10 seconds or so, even though there's no one there.
Oh, speaking of that, did you know that that little thing that you're recording with does not show up on Zoom when you are pulling it over on the screen?
Oh, yeah, I think I set the settings so that it wouldn't do that. But,
So, that was just information for you in case people are like, what are you talking about?
that is helpful. I didn't think about that as...
For
Yeah.
last class.
Yep.
But yeah.
Yeah, if I have it turned on, then it has this really weird, like a mirror and a mirror and a mirror and a mirror
no,
thing, and it creeps me
I
out.
100%
So,
understand why you did it. I'm just.
yeah. Oh, thank you. That is good to know. I will not show OBS anymore, but it is. I have it pulled up in front of me, making sure it's recording. That's all.
Yeah.
All right, we're going to get started then. So from empty models. So this is a big, longer title than what's on here. General multi-level models. So the word general in this means what? I think we talked about this very briefly last time. General has a very specific meaning. Normal distribution, exactly. So we're saying the level 1 E's have a normal distribution, and the level 2 U's will have a normal distribution. The E part is the general, though. Level 2 U's are always normal. So 2 levels, nested data, so not crossed. So a very specific context of persons nested in clusters is what we're talking about, where the outcome is plausibly continuous. All right, so 2 sides of a general linear model, making this a little more complete. Model for the means is this part. So this would be notation for a single level sampling design of people only. So beta 0, beta 1, and beta 2 are the fixed effects. They don't get p's because they're not variables, they're constants. So I'd have x1 that varies over people, x2 that varies over people, whatever else goes in the equation here. So I will keep calling these fixed effects. Fixed intercepts and fixed slopes are 2 particular kinds of fixed effects. Model for the variance then is what we're going to be focusing on, is extending this. So you are told that E is supposed to have a mean of 0 with a estimated variance. And the reason that it's only 1 is because the normal distribution has 1 variance to it. They're tied together. So that when you say E is normal, you're also saying E has constant variance because that's what normal means. Question?
Lisa, why the person's expected outcome is a weighted linear function?
Up
What
here?
Weighted, yes, what
I meant like what the slopes are essentially weighting this. Like so much of this variable plus so much of that variable.
Okay.
Yeah, that's how I would probably, like that's how I would explain a slope in more layman's term, is like a weight for that contribution. But yes, it's not the same as like a weight in like canonical correlation or like one of those things, like factor loadings, components and such, yep. So, question? No? Okay.
Is that the effective weight? Because we just learned from another class, effective weight.
I'm using weight in more of a colloquial sense here, but weight is a term for something that's estimated for a contribution to a linear combination more generally. So like in component analysis, you have weights. In discriminant function analysis, you have estimated weights. So, all right. So anyway, we're supposed to be told that E is normal, which means constant variance and independent. So we have to extend this anytime we have more than 1 dimension of sampling. That's when we know. So graphically then, empty model, single level, would look like this. So the line here is the grand mean for this histogram variable on its side here. If I want to predict what it is for this person down here, I would still use the grand mean as a starting point, but it's way wrong for them. They're way below average. So y hat here is the model for the means, and that's where the term comes from. Because you start with a common mean for everybody, and then you customize it based on the predictors that you enter into the model. But it's still a mean in the sense that people with the same profile get the same prediction. So model for the means is extending the variability in the means by adding in predictors. Model for the variance looks like this. So the variance of E at this point is the same thing as the variance of Y, because we're just deviating from the mean as y hat here. Cool. So this is all the variance that there is to be had. So let's take this from a single level example to a clustered picture. I've got a green cluster, a yellow cluster, and a purple cluster, okay? And so we're switching to PC. So same idea. if I don't know anything about a person, my best guess for their outcome is the grand mean of that outcome. That's going to be the fixed intercept. From there, though, I want to take advantage of the fact that I do know something about a person. I know what cluster they're from. So rather than giving everybody the same mean, I'm going to give them a cluster-specific version by adding in a random intercept. So here's my little two-level model here. So essentially what happens is U0 is the difference between the cluster mean and the mean of the cluster means. So the green group would have a positive U0, the yellow group would have a slightly negative one, and the purple group would have a more negative one. And we don't know or care what the actual U0 values are. I know, crazy. In the same way that we don't know or care what the individual E residuals are in a linear regression. What we keep track of is how much variance across clusters the random intercepts have. That's what the model parameter is that's being estimated directly. So whether you have 20 clusters or 200 clusters, you have a variance across them.
So with our first level of error, the E,
Yep.
those errors necessarily sum to 0.
Mm-hmm.
Okay. But that is not the case with the clusters, correct?
The
U's don't
U's
sum
have
to-
a mean of 0 too.
They do,
Yes, they have to.
okay,
Because what the mean would be is over here. It's given by the fixed effects.
okay.
Yep.
Just, okay.
So otherwise, the model would get more complex the more sample size we add. So we don't want that as a general property. So we care about the U0 variance, how much there was initially and how much it's been reduced by after we add cluster predictors. That's what we keep track of. You can ask for these U's to be predicted by the software. That is an option. But predicted is the right word. And I would highly discourage you from taking those U's and using them in subsequent analysis, because each U is then assumed to be perfectly reliable. Whereas in reality, some of these are going to be less reliable. So what happens is the estimated U's have what's known as a shrunken distribution. They're shoved to the mean. So clusters that are really small will have their U shoved more to what the fixed effects would predict, and clusters that are really discrepant, like extreme U's, will be shoved in as well. So we don't want the U's because they're predictions with error that we would want to take the error with us. If we do everything in one fell swoop, we can predict the U's through the model and answer research questions about what causes their variability through our predictors. I'm seeing some frowning.
Another question.
Okay.
So when you introduce the cluster level variance, does that impact that first level E variance? In other words, that the sum of it go from here to there?
It's literally taking like one pile and just splitting it into two. And if you added them back together, the total will be very close to what it would be in a single level model. Not the
Okay.
same, but very close.
Okay.
Yep.
Thank you.
Yep. And that's why I'd say you're not explaining variance, you're just splitting it into two
Mhm.
kinds. But the net total is still there. Did you have a question?
Yeah, but you might repeat it again, what part that we care about?
The part we care about.
Yeah.
Okay. The user means to an end. Like they're a representation of the idea that we're giving each cluster their own mean. What we care about is the variance across clusters in these U's. So we want to know how big this variance is, in particular, relative to the variance of the E's. So in other words, is the amount of variation that's due to what school you go to 10% of the information, or is it 50%?
Are you
And-
talking about discrepancy? That's what we're.
I'm heading towards a measure that's going to give a ratio, essentially, of the total variance, how much is between clusters.
Okay.
It's going to be called interclass correlation in just a couple slides here. But yeah, that's what you care about, is like, what is the relative breakdown? And then within each, how much of it went away by adding predictors targeting that source? So like I could say 10% of the variance in math has to do with what school you go to. And this is actually in a real example, 80% of that 10% has to do with how many kids get free lunch at your school. So those are the numbers I would hang on to, not what was the score for school A, and then for school B, and then for school C. Now, people do use the U's to make school-specific decisions. There's a, what's it called? It's a thing where they're trying to hold teachers accountable through multi-level modeling. What am I thinking of? What is it? Value added, thank you, that is what I'm thinking of. No, there's seriously a thing where they get multi-level data of multiple cohorts of students across years for teachers, and they try to estimate U's for teachers. And if you have a good one, then you're a good teacher, and if you have a low one, you're a bad teacher.
Bonuses or better pay or less pay.
And that goes towards their merit.
Yeah.
Which is crazy, because going back to your question about whether this has a mean of 0, yes it does, because everything that should be relevant in predicting how good you are should be in the fixed effects. So then it's like, did you get the model right such that I can actually make sense out of the U for this teacher, or is the model misspecified? Because students are not randomly assigned to their teachers. So it may be the case that more experienced teachers get the tougher teaching assignments because they're better able to handle it, which might make them look bad because their kids needed more help.
And they do worse.
Yeah, so it's a whole thing. But you care about how much variance of each kind and how well you did at explaining it. That's what we care.
So you report tau squared.
We would report this, but we would usually focus on how much of it went away as a proportion, and
Yes.
that's going to be called pseudo R square. Yeah, but yeah, you'd want to report the number. So that's between cluster variance. So each cluster gets its own version of U, and we pay attention to how much variance across clusters there is altogether. And then from there, each person gets their own E deviation from that cluster mean. And so then we have within cluster variance, represented by sigma squared, as intra-cluster differences to be explained. And we want to know the relative proportions of each of these things. Yep. Now note, there's only one symbol here. That means there's only one number. The model by default assumes that all clusters have the same amount of within cluster variability.
I was going to ask.
And that is kind of crazy if you think about it, but that's the assumption.
Okay. And that's homoscedasticity?
It is homoscedasticity across clusters. And that's what location scale models are designed to do differently. So the Hoffman and Walters article that I put for this week, the second half of that was written by Ryan Walters, former grad student, who decided to do his dissertation on location scale models. So,
Cool.
yeah, his comps was for him to write a Bayesian algorithm to estimate the models in R.
Awesome.
That was his comps project. And he said that the day that it finally worked, he just sat there staring at the number that matched what it was supposed to be for the first time in like 6 months, and just sat there for like 3 hours.
Just like, yay.
That is a good feeling. Like when the thing you're working on finally works like it's supposed to, that's best. But anywho, what he was interested in is covered in the second half of that chapter, which is location scale models, where you can what's the word I want? Put in, let's go with that. You can put in another kind of random intercept that covers differences in the size of the E variance across clusters. Another kind of cluster difference, not in the mean, but in this amount of E variance. Because one way that you could say a teacher is good is if maybe their students are less variable, right? If all the students are doing, like, not necessarily well, but you're bringing up the tail, like to close gaps, like that's a good thing, right?
So he was doing like sub EC on the variance.
Exactly.
Okay.
Yeah, like the amount of variance per cluster gets a linear model on it, where you can say clusters that have this property are more variable. Clusters that have this property are less variable. You can do all that. So just putting a pin in there. New notation, probably not the best thing at 136, but we'll look at it briefly and then we'll pretend we never saw it, and I'll do it again on Tuesday. How's that sound? That's a vocabulary word you should learn, by the way. There's review which is what it means, and then re-go over as an alternative. Re-go over means present it as if you've never seen it before. So we will re-go over this on Tuesday. But we are switching to a placeholder system of notation that looks like overkill at first, but once your models get real big, you'll be happy about it. So rather than have the fixed intercept directly in a level 1 equation like I have here, beta 0 C is what I have replaced this with. I want to point out 2 things. Number 1, we picked up a C. That makes it a variable.
Mm-hmm.
What does it vary over? Whatever C means.
Mm-hmm.
So this varies over clusters because of the C here. Subscripts are everything in multi-level models. You got to say what each predictor varies over. It is not red. It's not a parameter.
It's a random.
This beta 0 is, I call it a placeholder in my textbook. I call it a backpack because it holds things. It's holding these 2 terms that do reflect estimated parameters. It is a latent variable. Beta 0C is a circle for those of you in the SEM class or who have been through the SEM class. I know, this is going to break your brain.
Just started. We haven't been there yet. But
Yeah, user factor scores. And that's why you don't want to output them. So we have beta 0C now as its own level 2 equation. How does each cluster get their own version of the intercept is described by gamma, that's the Y looking thing here. Gamma 0, 0 is now my fixed intercept. Fixed effects are going to be gammas. U0C is still the random intercept. So putting together the mean of the cluster means plus the deviation from that for your cluster, remember U is how far off you are from that line, that gets you back to what the mean is for that cluster. So beta 0C holds the cluster means, and then it's decomposed with fixed and random effects. Then once each cluster gets their own mean, E is the discrepancy between that and the person's value, and then that gets us back to Y. So that's everything I just said. There. So there's really only 3 terms, which is why I say it looks like it's overkill. We have 1 fixed intercept, we have 1 within cluster variance at level 1, and we have 1 between cluster random intercept variance at level 2. All right, how are we doing? That's not so bad, right?
So do you do it that way as opposed to the composite equation in case you do have that cross level at some point that you're working with? Just help to clarify, what you're working with.
I think it's largely audience specific. Like pure stat would be much likely more do
Right,
a composite
what I was-
equation. In education, particularly folks that use like HLM software, like the output is shown in this kind of multi-level notation scheme, so it's a lot more like direct in that case. If I have, it depends on the design, honestly. So if I have a standard 2-level nested design or 3-level, I'll probably do hierarchical notation because I find it easier. But if it's crossed, it starts to fall apart real quick when you have multiple level 2s.
Right, because I'm like,
Then I just go down here.
Yeah.
So, yeah, the uglier it gets, the less likely I am to try to figure out all the levels.
To pull it apart.
Yep, I would.
Okay.
So one thing to keep in mind, folks, is that when I see people's written descriptions of these models, a common thing people screw up is they say, this right here, EPC, is the residual variance.
Mm-mm.
Why is that wrong?
Because that's working within a cluster, yes?
Yeah, where is residual variance on this slide? We'll play Where's Waldo. What symbol on this slide indicates level 1 residual variance? Yep. Level 1 residual means within cluster is the sigma squared. Okay, this is residual variance. This is a residual for that person, for that cluster. So you can say that E is a variable whose variance is that, but E is not residual variance. Same thing with U. This is not random intercept variance. this is the random intercept for cluster C specifically, whose variance is tau squared sub u sub 0. Yes. Also, something that drives me nuts is sometimes people switch the order of what comes first in level 1 and level 2, and then it's internally inconsistent across. Keep this locked. Don't do that.
1, 2, 3, as you build, you get longer.
You do. But they have to be in the same order or the system breaks down completely. So, like, I can't even tell you how many places I've seen, like, IT for longitudinal data, but then you go into the equation and the rest of it's TI. I'm like, you cannot do that. But, anywho. Yeah, it can get ugly real quick.
You count backwards.
There we go. All right. 142. I think that's enough for today. What do you think? Yeah, that's good. And we will re-go over this. Questions as we wrap up for the week.
For the location skill model that you talked about, could you give an example for like a research question that a location skill model would answer better?
Location scale example. So let's see here. Let's go with something like course evaluations, right? So that's nested data. I have course participants nested in instructors. And if I just have one semester's data, let's just go with that. Do you think everybody feels the same way about their experience in a class?
No.
Nope. Would you think that a lot of agreement means that maybe there's like, you can trust that a little more? Yeah, maybe. Do you think that there are reasons why some teachers are more polarizing than others?
Mm-hmm.
Would you have hypotheses about what those reasons could be?
Sure.
Sure. Then the idea of disagreement, polarity, that's level 1 residual variance. The more people disagree, the more variability there is within a cluster. And so you would essentially be building a linear model for predicting the amount of disagreement of the people who went to the same class or who have the same supervisor. In longitudinal data, you might think of something like adherence to medication. Are some people more adherent, meaning they're more consistent in how they take their medicines or do their practices of whatever, therapy, physical therapy, that kind of thing? Yep. So there's a lot of examples of hypotheses about variability. It's just we didn't have the tools to examine them. So this is like a newer, cool thing that I just want you to know about.
Yeah.
All right. Then let me know if you need anything. Please work on homework 0 if you haven't done so already. And have a good 3-day weekend. We'll see you next week.